Hello and welcome. I'm so glad you're here with me tonight. Whether you're returning from our other journeys or this is your first time, welcome to this peaceful space where we can let go of the day and drift gently towards sleep. Tonight, we're going somewhere extraordinary. We're not traveling through forests or oceans, not exploring dreams or the subconscious. Tonight, we're going to the smallest scales of reality, to the quantum realm, where the rules of everyday life dissolve and something utterly strange and beautiful emerges. We're going to explore quantum physics, but not in the way you might have experienced it in school. We're going to explore it gently, peacefully, letting the wonder and mystery of the quantum world wash over you like waves, carrying you softly towards sleep. Quantum physics is the science of the very small, the study of how matter and energy behave at the scale of atoms and subatomic particles. And at that scale, reality is nothing like our everyday experience. Particles can be in two places at once. They can tunnel through walls. They exist in states of possibility until observed. Empty space isn't empty at all, but seethes with energy and virtual particles popping in and out of existence. Time and space themselves become uncertain and fluid. It's a realm that seems almost magical, yet it's deeply real, confirmed by countless experiments and underlying all the technology we use every day. But here's what makes quantum physics perfect for falling asleep. It's so strange, so far removed from everyday intuition, that your logical mind can't quite grasp it. And when your logical mind encounters something it can't fully understand, something vast and mysterious, it starts to relax. It stops trying so hard, it lets go. And in that letting go, sleep can come. Over the next 4 hours, we're going to explore the quantum world together. We'll learn about the discoveries that revealed this hidden reality, about the paradoxes and puzzles that still fascinate physicists, about what quantum physics tells us about the nature of reality itself. We'll encounter uncertainty and entanglement, superposition and complementarity, wave functions, and probability clouds. We'll meet the scientists who discovered these strange phenomena and explore the philosophical implications of living in a quantum universe. But you don't need to understand any of it. You don't need to remember the details or follow every explanation. This isn't a physics lesson. This is a journey into mystery, into wonder, into the beautiful strangeness at the heart of reality. Let the words wash over you. Let the concepts dance at the edge of your understanding. Let yourself drift, and when sleep comes, welcome it. So settle in now. Get completely comfortable. Let your body sink into the softness beneath you. Take a slow, deep breath, hold it gently, and release it slowly. Feel your shoulders drop. Feel the tension leaving your body. Feel yourself beginning to relax. The quantum world is waiting for you. It's been there all along, hidden beneath the surface of everyday reality. And tonight, we're going to peek behind the curtain and see the universe as it really is. Strange, beautiful, mysterious, and ultimately beyond complete understanding. And in that mystery and that vastness, you'll find peace. Let's begin our journey into the quantum realm. Everything you can see, touch, and feel is made of atoms. Your body, the bed you're lying in, the air you're breathing, all of it is composed of atoms. And atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus at its center would be the size of a small marble on the 50-yard line, and the electrons would be tiny specks orbiting somewhere up in the highest seats. Everything in between, which is almost all of the atom, is empty space, which means that your body, is mostly empty space. The solidity you feel is an illusion created by electromagnetic forces between atoms. When you touch something, you're not actually touching it in the way you think. The electrons in your finger and the electrons in the object are repelling each other, and that repulsion is what you experience as touch. You never truly touch anything. It's all force fields and empty space, but atoms themselves are not the smallest things. They're made of smaller components, protons and neutrons in the nucleus, and electrons orbiting around it. And protons and neutrons are themselves made of even smaller particles called quarks. And at this scale, at the scale of quarks and electrons, the rules of classical physics break down completely. This is where quantum physics takes over, And this is where things get beautifully strange. The word quantum comes from the Latin word meaning how much, and it refers to the discrete, indivisible units that certain properties come in at the subatomic scale. Energy, for instance, doesn't come in a continuous range at the quantum level. It comes in discrete packets called quanta. An electron in an atom can't have just any energy. It can only have specific discrete energy levels, like steps on a staircase, rather than a smooth ramp. When an electron jumps from one energy level to another, it does so instantaneously without passing through the space in between. This is called a quantum leap, and it's one of the fundamental mysteries of quantum physics. How does the electron get from one place to another without traveling through the space between? No one really knows. This discovery that energy comes in discrete packets was the beginning of quantum physics. In the year 1900, a German physicist named Max Planck was trying to understand the spectrum of light emitted by hot objects. Classical physics couldn't explain the observations. The equations predicted something called the ultraviolet catastrophe, where infinite energy should be radiated at short wavelengths, which obviously doesn't happen. Planck found that if he assumed energy could only be emitted or absorbed in discrete packets, in quanta, the equations worked perfectly and matched the experimental observations. Planck himself didn't really believe in the physical reality of these quanta at first. He thought they were just a mathematical trick, a convenient assumption that made the math work. But the quanta were real, and this discovery opened the door to quantum physics. It was the first crack in the edifice of classical physics, the first hint that at small scales, nature operates by different rules than we're used to. Let your breathing slow now, deep and easy. Feel yourself relaxing more and more. Let's continue our gentle exploration of the quantum world. 5 years after Planck's discovery, in 1905, a young Albert Einstein published a paper explaining something called the photoelectric effect. When light shines on a metal surface, it can knock electrons loose from the metal. But classical physics couldn't explain all the details of this effect. Einstein showed that light, which everyone thought was a wave, also behaves like it's made of particles. He called these particles photons, and each photon carries a discrete quantum of energy. This was revolutionary because it meant that light has a dual nature. It's both a wave and a particle. How can something be both? It seems contradictory. Waves and particles are completely different things in our everyday experience. A wave is spread out through space. A particle is localized at a point. Yet light is somehow both. It exhibits wave-like behavior in some experiments and particle-like behavior in others. This is called wave-particle duality, and it's one of the central mysteries of quantum physics, and it's not just light. Everything has this dual nature. Electrons, which we usually think of as particles, also behave like waves. In fact, all matter has a wavelength associated with it, called the de Broglie wavelength, named after Louis de Broglie, who proposed this idea in 1924. For large objects like baseballs or people, the wavelength is so incredibly small that wave-like behavior is completely undetectable. But for tiny objects like electrons, the wave nature is significant and leads to observable effects. This wave-particle duality means that at the quantum level, the very concept of what a particle is becomes fuzzy and uncertain. Is an electron a particle that sometimes acts like a wave, or is it a wave that sometimes acts like a particle? Or is it something else entirely that we don't have a good word for, something that can exhibit both wave-like and particle-like properties depending on how we observe it? Quantum physics doesn't give us a clear answer. It just gives us the mathematics to predict what we'll observe, without necessarily explaining what's really going on beneath the observations. This uncertainty, this inability to form a clear mental picture of what's happening at the quantum level, can be frustrating if you approach it with your logical mind trying to understand completely. But tonight, let it be peaceful. Let it be okay not to fully understand. Let the mystery be beautiful rather than frustrating. Let yourself drift in that uncertainty and let it carry you towards sleep. In 1913, the Danish physicist Niels Bohr developed a model of the atom that incorporated quantum ideas. He proposed that electrons orbit the nucleus not in arbitrary orbits, but only in certain allowed orbits corresponding to specific energy levels. An electron could jump from one orbit to another by absorbing or emitting a photon of exactly the right energy, but it couldn't exist in between the allowed orbits. This explained why atoms emit and absorb light only at certain specific wavelengths, creating the characteristic spectral lines that had puzzled scientists for decades. Bohr's model was a major step forward, but it was still incomplete. It worked well for hydrogen, the simplest atom with just one electron, but it struggled with more complex atoms. It also couldn't explain why the allowed orbits were the ones they were. The model was descriptive, but it lacked a deeper underlying principle. It would take another decade and the work of several brilliant physicists to develop the more complete theory that we now call quantum mechanics. In the 1920s, quantum mechanics was developed through the work of physicists like Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others. This new theory provided a mathematical framework for describing quantum systems that was far more powerful and general than anything that had come before. And this theory made predictions that were even stranger than what had been discovered. So, Werner Heisenberg discovered what's now called the Heisenberg uncertainty principle in 1927. This principle states that there are fundamental limits to how precisely we can know certain pairs of properties of a quantum particle simultaneously. The most famous example is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measurement tools or techniques. It's a fundamental feature of reality itself at the quantum level. A particle simply doesn't have a precise position and a precise momentum simultaneously. Those properties are inherently uncertain, fuzzy, indeterminate. This was shocking when it was first proposed. It meant that the universe at its most fundamental level is not deterministic in the way that classical physics assumed. You can't know everything about a system, even in principle, and therefore you can't predict its future with certainty. The best you can do is calculate probabilities. Quantum mechanics is fundamentally probabilistic, giving us the odds of different outcomes rather than definite predictions. Einstein famously objected to this aspect of quantum mechanics, saying, "God does not play dice with the universe." He believed there must be some deeper level of reality, some hidden variables that we don't yet know about, that would restore determinism and eliminate the fundamental randomness that quantum mechanics seem to require. But decades of subsequent research, including clever experiments designed to test whether hidden variables could exist, have consistently supported quantum mechanics and its inherent randomness. It appears that at its deepest level, nature really does involve fundamental uncertainty and probability. Take a slow breath and let it out even more slowly. Feel how relaxed you are. Let's drift deeper into the quantum realm. Erwin Schrödinger developed a different mathematical formulation of quantum mechanics around the same time as Heisenberg, though Schrödinger's approach looked very different on the surface. Schrödinger's approach centered on what's called the wave function, a mathematical entity that describes the quantum state of a system. The wave function evolves over time according to an equation called the Schrödinger equation, and from the wave function, you can calculate the probability of finding a particle in any given location or with any given property. The wave function itself is not something you can directly observe or measure. It's an abstract mathematical object, a tool for making predictions, but it contains all the information about a quantum system, and it evolves in a deterministic way according to the Schrödinger equation. The randomness comes in when you make a measurement. The act of measurement causes what's called the collapse of the wave function. Before measurement, the wave function describes a superposition of many possible states. After measurement, the wave function collapses to just one of those possibilities, and which one you get is random, determined only by the probabilities encoded in the wave function. This raises profound questions about the role of observation in quantum mechanics. What counts as a measurement? Does it require a conscious observer, or will any interaction with a larger system cause collapse? And what exactly happens during the collapse? Does the wave function really collapse, physically changing in an instant? Or is the collapse just a way of describing our updated knowledge after learning the outcome of a measurement? These questions, bundled together under the heading of the measurement problem, remain controversial and are part of what's called the interpretation of quantum mechanics. The most widely taught interpretation is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. According to this interpretation, the wave function is not a description of physical reality itself, but rather a description of our knowledge or information about the system. Before measurement, multiple possibilities exist in superposition, not in the sense that the particle literally exists in multiple states simultaneously, but in the sense that the outcome is genuinely undetermined. Measurement reveals which outcome has occurred, and the wave function collapses to reflect this new knowledge. But there are other interpretations. The many worlds interpretation proposed by Hugh Everett in 1957 suggests that the wave function never collapses. Instead, every possible outcome of a quantum measurement actually occurs, but in different branches of reality. When you measure a quantum system, the universe splits into multiple versions, one for each possible outcome, and you experience just one branch, while other versions of you experience the other branches. According to many worlds, every quantum possibility is realized somewhere in the vast multiverse of branching realities. This might sound like science fiction, but it's a legitimate interpretation of quantum mechanics that some physicists take seriously. It avoids the problem of wave function collapse by saying there is no collapse. The wave function just keeps evolving smoothly according to the Schrödinger equation, describing a reality that's constantly branching into more and more versions. From our perspective within one branch, it looks like collapse and randomness. But from a God's eye view of the entire wave function, everything is deterministic and all possibilities are realized. Then there are pilot wave theories, which propose that particles have definite positions at all times, guided by a quantum wave field. There's the transactional interpretation, which involves waves going forward and backward in time. There's quantum Bayesianism, or cubism, which treats quantum mechanics as a tool for making bets about future observations, rather than as a description of objective reality. And there are others. The fact that quantum mechanics can be interpreted in so many different ways, all consistent with the experimental evidence, shows how mysterious and profound it is. You don't need to choose an interpretation or decide which one is right. Just let the mystery be. Let your mind touch these ideas lightly without grasping, and let yourself drift peacefully. One of the most famous thought experiments in quantum mechanics is Schrödinger's cat, proposed by Erwin Schrödinger in 1935 as a way of illustrating what he saw as the absurdity of the Copenhagen interpretation. Imagine a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The experiment is set up so that if the atom decays, the Geiger counter detects it, triggers the hammer, which breaks the vial, releasing the poison and killing the cat. According to quantum mechanics, the atom exists in a superposition of decayed and not decayed states until observed. If you apply quantum mechanics to the entire system, then the cat must also exist in a superposition of alive and dead states until you open the box and look. But this seems absurd. How can a cat be both alive and dead? Cats are macroscopic objects, and our everyday experience tells us that things are definitely one way or another, not in superposition. Schrödinger intended this thought experiment as a criticism of quantum mechanics, highlighting what he saw as a problem with applying quantum rules to large systems. But it's since become one of the most famous illustrations of quantum weirdness. It raises the question of where the boundary is between the quantum world of superposition and the classical world of definite states. When does a quantum system become large enough that superposition breaks down and definite classical behavior emerges? This is called the quantum to classical transition, or the problem of decoherence. Decoherence is the process by which quantum superpositions are destroyed through interaction with the environment. When a quantum system interacts with its surroundings, Information about the system leaks into the environment, and this causes the different possibilities in the superposition to become effectively separated, making the system behave classically. For something as large and warm and interacting with its environment as a cat, decoherence happens essentially instantaneously. The cat is never truly in superposition in any meaningful sense because decoherence destroys the superposition long before we open the box. But decoherence doesn't solve all the puzzles. It explains why large objects don't appear to be in superposition, but it doesn't really solve the measurement problem. It doesn't tell us why we experience one definite outcome rather than a continued awareness of multiple possibilities. The different interpretations of quantum mechanics offer different answers to this question, or in some cases suggest the question is misguided. For now, as you lie here relaxed and peaceful, just appreciate the strangeness. Somewhere at the boundary between the quantum and classical worlds, definiteness emerges from possibility. One reality crystallizes out of many potential realities, and the bizarre quantum realm gives way to the familiar classical world we experience. How this happens remains one of the deepest mysteries in physics. Your breathing is so slow now, so peaceful. Let yourself sink deeper into relaxation. Let's continue exploring the quantum world. One of the strangest and most counterintuitive features of quantum mechanics is entanglement. When two quantum particles interact, they can become entangled, meaning their quantum states become correlated in ways that have no classical analog. Once entangled, the particles remain connected no matter how far apart they are. If you measure one particle and find it has a particular property, the other particle will instantly have a corresponding property, even if it's on the other side of the universe. Einstein called this spooky action at a distance, and thought it showed that quantum mechanics must be incomplete. How could measuring one particle instantaneously affect another particle far away? That would seem to require faster-than-light communication, which Einstein's theory of relativity says is impossible. Einstein, along with physicists Boris Podolsky and Nathan Rosen, proposed a thought experiment in 1935 now called the EPR paradox, arguing that quantum mechanics must be missing something, that there must be hidden variables that determine the outcomes of measurements in advance, making the correlations between entangled particles less mysterious. But in 1964, the physicist John Bell proved a remarkable theorem. Bell showed that if hidden variables exist, they would have to produce correlations that obey certain mathematical constraints called Bell inequalities, and he showed that quantum mechanics predicts violations of these inequalities. This meant that experiments could actually test whether hidden variables exist. If the experiments showed violations of Bell inequalities consistent with quantum mechanics, then hidden variables of the type Einstein imagined don't exist. The experiments were done, starting in the 1970s and continuing with increasing sophistication to the present day. They consistently show violations of Bell inequalities exactly as quantum mechanics predicts. Entanglement is real. The correlations between entangled particles really are stronger than anything that could be explained by hidden variables or by any local theory where influences travel at or below the speed of light. The universe is fundamentally non-local in a way that has no classical explanation, but, and this is important, the entanglement doesn't allow faster-than-light communication. When you measure an entangled particle, you get a random result. The fact that this result is correlated with a measurement on the distant particle doesn't help you send information because you can't control what result you get. The correlations only become apparent when the two parties compare their results later, which has to be done through normal, slower-than-light communication. So entanglement doesn't violate relativity. It's weird and non-local, but it doesn't allow signaling faster than light. Entanglement is now not just a philosophical puzzle, but a resource used in emerging quantum technologies. Quantum cryptography uses entanglement to create communication channels that are fundamentally secure against eavesdropping. Quantum computers use entanglement to perform certain calculations exponentially faster than classical computers. Quantum teleportation, which has been demonstrated in laboratories, uses entanglement to transfer the quantum state of one particle to another particle far away, though again without faster-than-light communication. The fact that entanglement is real and useful makes it less spooky in some ways. It's just a feature of how quantum systems work, a feature that we're learning to harness. But in another way, it remains deeply mysterious. What does it mean that two particles can be so intimately connected across arbitrary distances? What does this tell us about the nature of space and reality? These are questions that physicists and philosophers continue to ponder. Feel yourself drifting deeper, deeper into peace. The quantum world is strange and mysterious, and you don't need to understand it all. Just let it be. Let's continue. Quantum tunneling is also crucial for modern electronics. The transistors in computer chips work because of quantum tunneling effects. As we make electronic devices smaller and smaller, quantum effects become more and more important, and engineers have to take quantum mechanics into account in their designs. In your own body, quantum tunneling plays a role in how enzymes work. Some enzyme reactions involve hydrogen atoms tunneling through barriers, allowing reactions to occur much faster than they would classically. There's even speculation that quantum effects might be important in biological processes like photosynthesis, where energy is transferred with remarkable efficiency, and possibly in bird navigation, where birds might use quantum entanglement in their eyes to sense magnetic fields. The quantum world isn't separate from the everyday world. It underlies everything. You're made of quantum particles following quantum rules. The solidity of matter, the chemistry that makes life possible, the light that lets you see, all of it arises from quantum mechanics. The classical world we experience is an emergent phenomenon, arising from the quantum substrate when countless quantum particles interact in ways that average out the quantum weirdness. Let your breathing be soft and easy. Let these ideas float through your mind like clouds without grasping them. Let yourself drift. One of the most beautiful and profound principles in quantum mechanics is the principle of complementarity, articulated by Niels Bohr. Complementarity is the idea that quantum objects have pairs of properties that are mutually exclusive, but both necessary for a complete description. Wave and particle are complementary descriptions. You can observe wave-like behavior or particle-like behavior, but not both simultaneously. Position and momentum are complementary. You can precisely know one or the other, but not both. These aren't just limitations of measurement. They reflect something fundamental about the nature of quantum reality. Bohr argued that we need both complementary descriptions to fully understand quantum phenomena, even though they seem contradictory from a classical perspective. A complete description requires holding apparently contradictory ideas in mind simultaneously, accepting that reality at the quantum level is more subtle and complex than our everyday intuition suggests. There's something almost philosophical or spiritual about this. The universe, at its deepest level, resists being fully captured by any single description or perspective. It requires multiple complementary views, each valid in its context, but none complete on its own. This has parallels in other areas of life and thought, where truth often lies not in choosing one perspective over another, but in holding multiple perspectives simultaneously and recognizing that reality is richer than any single viewpoint can capture. Another profound concept in quantum mechanics is the principle of superposition. Before a quantum system is measured, it exists in a superposition of all possible states, weighted by their probabilities. The system isn't in one state or another. It's in a combination of states, all existing simultaneously in potential. Only when measured does the system take on a definite state. This is often illustrated with the concept of quantum bits or qubits, the basic units of quantum computers. A classical bit is either 0 or 1. A qubit can be in a superposition of 0 and 1, existing in both states at once with certain probabilities. Multiple qubits can be entangled, creating superpositions of an exponentially large number of possible states. This is what gives quantum computers their potential power for certain types of calculations, but superposition is delicate. Interaction with the environment causes decoherence, destroying the superposition and collapsing the system into a definite classical state. This is the major technical challenge in building practical quantum computers. Maintaining quantum superposition long enough to perform useful calculations while isolating the system from environmental disturbances that would cause decoherence. The fragility of quantum superposition might also explain why we don't see quantum effects at macroscopic scales. It's not that quantum mechanics stops applying to large objects. It's that large objects interact so strongly with their environments that decoherence happens almost instantaneously, making them behave classically. The quantum world is hidden not because it's far away, but because it's fragile and easily disrupted. This fragility has a certain poetry to it. The quantum realm is a delicate reality, easily disturbed, existing in a state of pure potential that collapses into actuality at the slightest touch. It's like a dream that vanishes upon waking, leaving only traces and effects but never directly experienced in waking consciousness. We live in the classical world that emerges from the quantum substrate, and we can only know the quantum world indirectly, through its effects and through the mathematical formalism that describes it. Your body is so heavy now, so relaxed. Your mind is quiet, drifting peacefully. Let's explore just a bit more of the quantum world and then let you drift completely into sleep. The concept of the vacuum in quantum mechanics is radically different from the classical idea of empty space. In quantum field theory, which extends quantum mechanics to include special relativity, the vacuum is not empty. It's seething with activity, with virtual particles constantly popping in and out of existence. These virtual particles are quantum fluctuations, temporary violations of energy conservation, allowed by Heisenberg's uncertainty principle. A particle and its antiparticle can spontaneously appear, exist for a brief moment, and then annihilate each other, all happening so quickly that the uncertainty principle allows it. This might sound like pure theory, but vacuum fluctuations have measurable effects. The Casimir effect, predicted in 1948 and confirmed experimentally, arises from vacuum fluctuations. When two uncharged metal plates are placed very close together in a vacuum, they experience an attractive force. This force arises because the vacuum fluctuations between the plates are restricted by the boundary conditions. So there's a difference in vacuum energy inside and outside the plates, creating a net force. Vacuum fluctuations also cause what's called the Lamb shift, a tiny shift in the energy levels of hydrogen atoms. And there are theoretical arguments that vacuum fluctuations might contribute to the cosmological constant, the mysterious dark energy that's causing the universe's expansion to accelerate. Though there are enormous unsolved problems with these calculations, the quantum vacuum is not nothing. It's a dynamic active medium full of energy and virtual particles. In a sense, the quantum vacuum is the closest thing to nothing that can exist, yet it's not truly nothing. It has properties, structure, and energy. This raises profound philosophical questions about the nature of existence and nothingness. Can true nothingness exist? Or is the quantum vacuum, buzzing with potential and fluctuations, the most fundamental state of reality? These are questions at the boundary of physics and philosophy, where science touches on ancient metaphysical puzzles about being and non-being. Quantum mechanics doesn't answer these questions definitively, but it reframes them, showing that even our concept of nothing needs to be revised in light of quantum reality. The uncertainty principle, which we touched on earlier, deserves deeper exploration because it's so fundamental and so often misunderstood. The uncertainty principle is not about disturbance caused by measurement, though that's a common misconception. It's not that measuring a particle's position disturbs its momentum. Rather, the uncertainty principle says that a particle simply doesn't have both a precise position and a precise momentum simultaneously. These properties are incompatible. The more defined one is, the less defined the other can be. This is related to the wave nature of quantum particles. A wave that's localized in space, like a pulse, necessarily contains a range of frequencies or wavelengths, A wave with a definite wavelength necessarily extends through space. Since momentum is related to wavelength in quantum mechanics, a particle with well-defined position has uncertain momentum, and vice versa. The uncertainty principle is a consequence of the wave nature of matter, a fundamental feature of how waves work. There are other pairs of properties that obey uncertainty relations. Energy and time are uncertain in a complementary way. If you want to measure the energy of a system very precisely, it takes a long time. If you want to measure it quickly, there's more uncertainty in the energy. This has practical consequences. It means that short-lived particles can have uncertain masses, and it allows for temporary violations of energy conservation through quantum fluctuations, as long as they're brief enough. The uncertainty principle has profound implications for determinism and causality. Classical physics was deterministic. If you knew the exact state of a system, you could predict its future with certainty. Quantum mechanics is fundamentally different. Even with perfect knowledge of a system's quantum state, described by its wave function, you can only predict probabilities of future outcomes. The universe at its core involves irreducible randomness. God does play dice, despite Einstein's objections. But quantum randomness is not the same as classical randomness arising from ignorance. Classical randomness, like rolling dice, is really deterministic if you know all the details precisely enough. The dice follow deterministic laws of motion. They only appear random because we can't track all the details. Quantum randomness is different. It's not due to hidden variables or missing information. It's fundamental. The outcome of a quantum measurement is genuinely undetermined until it happens. This is unsettling to our deterministic intuitions, but it appears to be how reality actually works. Some physicists and philosophers find this liberating rather than disturbing. If the universe is fundamentally probabilistic at its base, then the future is genuinely open, not predetermined. There's room for novelty, for genuine chance, for possibilities that aren't already written into the initial conditions of the universe. Whether this has implications for free will is a matter of ongoing philosophical debate, but it at least means that the universe is not a clockwork mechanism grinding out a predetermined future. Let yourself relax even more. Your breathing is so slow and steady. Your body is heavy and comfortable. We're going to drift through a few more quantum concepts and then let you fall completely into sleep. Quantum mechanics has many counterintuitive features, but one of the strangest might be what's called the quantum Zeno effect, named after Zeno of Elea, who proposed famous paradoxes about motion. The quantum Zeno effect says that if you continuously observe a quantum system, you can prevent it from evolving. A watched quantum pot never boils. This happens because measurement collapses the wave function. If you're constantly measuring a system, constantly collapsing its wave function back to its initial state, it never has time to evolve into other states. You can literally freeze a quantum system by watching it closely enough. This has been demonstrated experimentally. By repeatedly measuring an unstable particle, you can prevent it from decaying, dramatically increasing its lifetime. There is also a related effect called the quantum anti-Zeno effect, where frequent measurements can actually speed up evolution instead of slowing it down, depending on the details of how the measurements are done. These effects show how deeply measurement is woven into the fabric of quantum reality. Observation isn't passive in the quantum world. It actively affects what's observed. This raises fascinating philosophical questions. If observation affects reality, what counts as an observation? Does it require consciousness, or is any interaction sufficient? Most physicists think consciousness is not required, that any interaction that causes decoherence counts. But there are some, particularly those influenced by certain interpretations of quantum mechanics, who think consciousness might play a special role. These ideas remain speculative and controversial, but they point to the deep puzzles about the relationship between mind and matter that quantum mechanics raises. The double-slit experiment is perhaps the most famous demonstration of quantum weirdness. It's been called the central mystery of quantum mechanics, containing within it all the strangeness of the quantum world. The experiment is simple in concept. You have a source that emits particles, like electrons, one at a time. The particles travel toward a barrier with two narrow slits cut in it. Beyond the barrier is a detector screen that records where the particles hit. If you close one slit and send particles through the other, they form a pattern on the screen corresponding to particles going straight through the open slit. Same if you close the first slit and open the second. But if you open both slits and send particles through one at a time, something strange happens. Even though each particle goes through one slit or the other, the pattern that builds up on the screen is an interference pattern with alternating bright and dark bands. This is the pattern you'd expect from waves, not particles. Each individual particle somehow interferes with itself, as if it went through both slits simultaneously. The particle acts like a wave, spreading out and going through both slits, interfering with itself, and then acting like a particle again when it hits the screen at a definite point. Wave-particle duality is on full display, but here's where it gets even stranger. If you put detectors at the slits to see which slit each particle actually goes through, the interference pattern disappears. With the detectors on, you see two simple bands on the screen, just what you'd expect from particles going through one slit or the other. The act of observing which slit the particle goes through destroys the interference pattern. It's as if the particle knows it's being watched and changes its behavior accordingly. This isn't because the detectors physically disturb the particles, though that was the initial explanation. Even very gentle detection methods that minimize disturbance still destroy the interference pattern. The issue is more subtle. When you measure which slit the particle goes through, you gain information that's incompatible with the interference pattern. You can't have both the which path information and the interference pattern. They're complementary aspects of reality. Trying to observe one destroys the other. The double-slit experiment has been performed with photons, electrons, atoms, and even large molecules containing hundreds of atoms. The results are always the same. Individual particles produce interference patterns characteristic of waves when both slits are open and unobserved. The pattern emerges particle by particle, dot by dot, each particle adding 1 point to the screen, but somehow the overall pattern is an interference pattern. An observation of which slit the particle goes through destroys the interference. This experiment captures the essential mystery of quantum mechanics. How can a particle be in a superposition of going through both slits? What does it mean for something to exist in two places at once? How does observation change what happens? These questions have no simple answers that don't challenge our basic intuitions about reality. Niels Bohr, when asked if the double-slit experiment revealed the true nature of reality, replied that there is no quantum reality. There are only quantum observations. According to Bohr's Copenhagen interpretation, we shouldn't try to picture what's really happening between measurements. We should only talk about the results of measurements. The wave function is not a description of reality, but a tool for calculating probabilities of measurement outcomes. This instrumentalist approach avoids the puzzles by refusing to make claims about what's really happening when we're not looking. But many physicists find this unsatisfying. It seems to make consciousness or observation central to reality in a way that feels arbitrary. Other interpretations, like the many worlds interpretation, provide different answers. In many worlds, the particle really does go through both slits, but the universe splits into branches where it went through one slit and branches where it went through the other. We experience only one branch, but both are equally real. The interference pattern emerges from the mathematical overlap of these branches. Observation doesn't destroy the interference. It just causes the branches to become too different to interfere with each other anymore. These different interpretations, all mathematically equivalent in their predictions, show that quantum mechanics is not just physics, but also philosophy. It forces us to think deeply about the nature of reality, observation, causality, and even the role of consciousness in the universe. Let your breathing be soft and gentle. Let these mysteries wash over you without grasping them. Let yourself drift deeper into peace. Quantum entanglement, which we discussed earlier, has been extended to larger and larger systems in recent experiments. Entanglement was once thought to be a delicate phenomenon that could only be demonstrated with individual particles in carefully controlled laboratory conditions. But physicists have now created entanglement between photons separated by hundreds of kilometers, between atoms in different laboratories, and even between small mechanical oscillators visible to the naked eye. In 2019, physicists at the National Institute of Standards and Technology entangled two small mechanical drums, objects containing billions of atoms, demonstrating quantum effects at a scale approaching everyday experience. While we're still far from entangling anything as large as a cat, these experiments show that quantum mechanics applies at larger scales than we once thought possible. The boundary between quantum and classical is not as sharp as we once believed. There's also been progress in quantum biology, the study of whether quantum effects play functional roles in biological systems. For a long time, most biologists assumed that living systems were too warm, wet, and noisy for quantum effects to persist long enough to matter. But evidence has accumulated that quantum phenomena might be important in photosynthesis, where energy is transferred between molecules with remarkably high efficiency. Some researchers think quantum coherence might allow plants to explore multiple energy transfer pathways simultaneously, finding the most efficient route through quantum superposition. There's also evidence that birds might use quantum entanglement to sense magnetic fields for navigation. Birds have a protein in their eyes called cryptochrome that contains pairs of electrons that become entangled when exposed to blue light. The Earth's magnetic field affects these entangled electrons differently depending on their orientation, potentially allowing the bird to see the magnetic field as a pattern overlaid on their visual perception. This remains somewhat controversial and is an active area of research, but if confirmed, it would mean that quantum entanglement is being used by birds every time they migrate, that this most exotic quantum phenomenon is happening in millions of birds' eyes as they fly. Even human consciousness might involve quantum effects, though this is highly speculative. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that consciousness arises from quantum computations in cellular structures called microtubules inside neurons. According to their theory, quantum superposition and collapse in microtubules is what generates conscious experience. This theory is not widely accepted and faces significant challenges, but it represents an attempt to explain consciousness using quantum mechanics. Whether or not this particular theory is correct, the fact that serious scientists are exploring quantum approaches to consciousness shows how deeply quantum mechanics challenges our understanding of fundamental phenomena. The quantum world and the everyday world are not as separate as we once thought. Quantum effects underlie all of chemistry, all of biology, all of the physical processes that make life and consciousness possible. We are quantum beings living in a quantum universe, and the classical world we experience is an approximation, a useful simplification that works at large scales but isn't the deep truth. This has a certain beauty to it. The universe is stranger, more mysterious, more wonderful than our everyday experience suggests. Beneath the surface of ordinary reality is a realm of possibility, superposition, entanglement, and uncertainty. We can't directly perceive this realm with our senses, but we can discover it through careful experiments and mathematical reasoning. And in discovering it, we learn something profound about the nature of existence itself. Your body is so relaxed now, so comfortable. Your mind is drifting peacefully. Let's explore a few more aspects of quantum reality, and then let you fall completely into sleep. Quantum field theory, developed in the mid-20th century, extends quantum mechanics to describe fields rather than just particles. In quantum field theory, particles are excitations of underlying fields that fill all of space. The electromagnetic field, for instance, pervades space, and photons are ripples or excitations in this field. Similarly, there are electron fields, quark fields, and fields for all the other fundamental particles. This represents a profound shift in how we think about particles. Particles are not primary objects traveling through empty space. Space is filled with fields, and particles are just localized excitations of these fields. When a particle is created, the field increases in excitation. When a particle is destroyed, the excitation decreases. Particles can be created and destroyed, but the fields are eternal and fundamental. Quantum field theory combines quantum mechanics with special relativity, Einstein's theory of space and time. This combination leads to predictions that have been confirmed with extraordinary precision. The most precisely tested prediction in all of science is the magnetic moment of the electron, calculated using quantum electrodynamics, the quantum field theory of electromagnetism. The theoretical prediction and experimental measurement agree to more than 10 decimal places, an astonishing achievement that shows how accurate quantum field theory is. But quantum field theory also leads to some puzzling infinities that have to be dealt with through a process called renormalization. When you try to calculate certain quantities, like the energy of the vacuum or the mass of a particle, the equations give infinite answers. Through renormalization, physicists absorb these infinities into redefined constants, arriving at finite measurable predictions. This process works brilliantly in practice, but has a somewhat ad hoc character that bothers some physicists. It suggests that quantum field theory, despite its successes, might not be the final theory but an approximation to something deeper. The standard model of particle physics, our best current theory of fundamental particles and forces, is a quantum field theory. It describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It describes all the known fundamental particles, 6 quarks, 6 leptons, including the electron, force-carrying particles like the photon and gluon, and the Higgs boson. The standard model has been tested extensively and has been remarkably successful, predicting the existence of particles before they were discovered and agreeing with experiments to high precision. But the standard model is incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It has parameters that have to be measured rather than derived from deeper principles. And it breaks down at extremely high energies or small distances, where quantum effects of gravity become important. We know there must be a more fundamental theory that includes both quantum mechanics and gravity, but we don't yet know what that theory is. String theory is one attempt to unify quantum mechanics and gravity. In string theory, the fundamental constituents of reality are not point particles but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. A string vibrating one way appears as an electron, vibrating another way as a photon, and so on. String theory naturally includes gravity, with gravitons arising as particular string vibrations. It also requires extra dimensions of space beyond the 3 we experience, with these extra dimensions curled up too small to perceive directly. String theory is mathematically rich and beautiful, but it faces significant challenges. It has not yet made testable predictions that would distinguish it from other theories. The energies needed to directly probe string scales are far beyond any conceivable experiment, and there appear to be an enormous number of possible string theory solutions, perhaps 10 by 500 or more, leading to a landscape of possible universes with different properties. Some see this as a strength, allowing string theory to potentially explain why our universe has the properties it does. Others see it as a weakness, making the theory unfalsifiable and unscientific. Loop quantum gravity is another approach to quantum gravity. Instead of strings, it focuses on the fabric of space-time itself, proposing that space is not continuous but has a granular structure at the smallest scales. Space is woven from loops or networks, with area and volume coming in discrete quantum units. Time also becomes discrete in some formulations. Loop quantum gravity doesn't require extra dimensions and is more closely connected to Einstein's general relativity, but it faces its own challenges in making contact with experiments and in describing all the particles and forces we observe. These are active areas of research, with brilliant physicists working on them, but we don't yet know which, if any, of these approaches is correct. We may need entirely new ideas, new mathematical structures, new ways of thinking about space, time, and matter. The fact that we've been working on quantum gravity for decades without a clear answer shows how difficult the problem is and how much we still don't understand. about the deepest nature of reality. But this is okay. Science is an ongoing process, not a completed edifice. Each generation of physicists builds on the work of previous generations, discovering new phenomena, developing new theories, and pushing the boundaries of understanding further. The quantum revolution that began in 1900 with Planck's discovery of quanta is still unfolding, still revealing new surprises, still showing us that reality is stranger than we imagined, and you don't need to understand it all or solve these problems. Just rest in the mystery, rest in the wonder. Let the universe be vast and incomprehensible, and let that be beautiful rather than frustrating. Your breathing is so slow, so peaceful. You're drifting in a quantum superposition between waking and sleeping, between consciousness and dreams. Let yourself collapse into the sleeping state. Let go. One of the most philosophically intriguing aspects of quantum mechanics is what it might tell us about the nature of reality itself. Does reality exist independently of observation, or does observation somehow create reality? This question has been debated since the early days of quantum mechanics and remains controversial. The realist view holds that reality exists objectively, independently of whether anyone is observing it. The quantum wave function describes this objective reality, even if we can't fully visualize what it's describing. Measurement reveals pre-existing properties rather than creating them. Most physicists probably lean towards some form of realism, though quantum mechanics makes it harder to maintain naive realism, where objects have definite properties at all times. The anti-realist or instrumentalist view, associated with the Copenhagen interpretation, holds that we shouldn't make claims about reality beyond what we can observe. The wave function is just a mathematical tool for making predictions, not a description of objective reality. Questions about what's really happening when we're not looking are meaningless or at least beyond the scope of science. This view avoids many conceptual puzzles, but seems to make observation and measurement central in a way that many find uncomfortable. Participatory anthropic principle, proposed by physicist John Wheeler, suggests that observers are not just passive recipients of information, but active participants in bringing reality into being. In Wheeler's words, we live in a participatory universe. Observation doesn't just reveal reality, it actualizes reality, collapsing potentiality into actuality. This is inspired by quantum mechanics, but goes beyond what the equations strictly require, adding a philosophical interpretation about the role of consciousness or observation in the cosmos. These different philosophical stances can't be decided by experiment, at least not with current technology. They are interpretations of the mathematical formalism, different ways of thinking about what the equations mean. Some physicists think these questions are important and worth debating. Others think they're distractions from the real work of physics, which is to make predictions and test them experimentally. But the questions persist because quantum mechanics, unlike classical physics, doesn't give us an obvious picture of reality. It forces us to think carefully about what we mean by reality, observation, and existence. One intriguing thought experiment is the delayed choice experiment, a variant of the double-slit experiment proposed by John Wheeler. In this experiment, you can choose whether to measure which slit a particle went through, or let it interfere and show wave-like behavior. But you make this choice after the particle has already passed through the slits. Remarkably, experiments show that your delayed choice affects what happened in the past. If you choose to measure which slit, the particle behaves as if it went through one slit. If you choose not to measure, it behaves as if it went through both and interferes with itself. This doesn't mean you can send information to the past or change history. The results are still consistent with normal causality, but it does show that the past is not fixed in the way we usually think. The particle's behavior is not determined at the moment it goes through the slits, but only when the entire experimental setup, including the final measurement, is complete. Past and present are entangled in a way that challenges our linear notion of time and causality. Quantum mechanics might be telling us that time is not what we think it is, that the division of events into past, present, and future is more fluid at the quantum level than it appears in everyday life. Some interpretations of quantum mechanics, like the transactional interpretation, explicitly involve influences traveling backward in time to make sense of phenomena like entanglement. Others, like many worlds, suggest that time is an emergent property arising from the growth of entanglement as the universal wave function evolves. These are deep waters, touching on questions about the nature of time that philosophers have pondered for millennia. Quantum mechanics doesn't answer these questions definitively, but it reframes them, showing that our intuitive understanding of time is incomplete at best. Let yourself drift even deeper now. Time is dissolving. Past and future are fading. There is only this moment, this breath, this gentle descent into sleep. The measurement problem, which we've touched on several times, remains one of the most vexing issues in quantum mechanics. The problem is this. According to the Schrödinger equation, the wave function evolves smoothly and deterministically. But when we make a measurement, the wave function appears to collapse suddenly and randomly to one outcome. Where does this collapse come from? What causes it? When exactly does it happen? The Schrödinger equation doesn't include collapse. It's added as a separate postulate, which makes the theory feel incomplete. Some interpretations, like many worlds, solve this by saying there is no collapse. Others, like pilot wave theories, avoid collapse by giving particles definite positions at all times. Some theories, like objective collapse theories, modify quantum mechanics to include actual physical collapse mechanisms triggered when quantum superpositions reach a certain size or complexity. These theories make slightly different predictions from standard quantum mechanics, predictions that might eventually be tested. One such theory is the Ghirardi-Rimini-Weber (GRW) theory, which adds spontaneous collapse events to the Schrödinger equation. Individual particles collapse rarely, so quantum superpositions can persist for small systems. But large systems with many particles collapse almost continuously, explaining why we don't see macroscopic superpositions. The collapse is a real physical process, not just a change in our knowledge. This theory has been tested experimentally, and so far the results are consistent with it, though they don't yet rule out standard quantum mechanics either. The measurement problem is closely related to the quantum to classical transition. Why does the quantum world of superposition and uncertainty give way to the classical world of definite outcomes that we experience? Decoherence, which we discussed earlier, explains much of this transition, but doesn't completely solve the measurement problem. Decoherence explains why different outcomes become effectively separated and can't interfere. But it doesn't explain why we experience one definite outcome rather than remaining in a superposition of experiencing all outcomes. These are hard problems, and physicists and philosophers have been working on them for nearly a century without complete consensus. But that's okay. Some problems are genuinely difficult, and it's honest to admit when we don't have all the answers. The fact that we can identify these problems, formulate them precisely, and make progress on them even if we haven't solved them completely is itself an achievement. And for you, lying here peacefully, these unsolved problems don't matter. Let the physicists worry about them. You can simply rest in the mystery, appreciating that reality at its deepest level is more strange and wonderful than we fully understand. Your body is so heavy, so relaxed. Your mind is quiet, drifting like a quantum particle in superposition, neither fully awake nor fully asleep, existing in that peaceful in-between state. Quantum mechanics has practical applications that touch your life every day, even if you're not aware of them. The device you're listening to this on, whether it's a phone or computer or tablet, relies on quantum mechanics in its fundamental operation. The transistors that make up computer chips are based on quantum tunneling. The lasers used in fiber optic communication rely on quantum properties of atoms and light. LEDs, solar panels, MRI machines, atomic clocks that make GPS possible, all of these technologies are applications of quantum mechanics. Quantum cryptography is being developed to create communication systems that are fundamentally secure, where any attempt at eavesdropping would disturb the quantum states being transmitted and be immediately detected. Some companies and governments are already deploying quantum key distribution systems for highly secure communications. Quantum sensors can measure tiny changes in magnetic fields, gravity, or time with unprecedented precision. These sensors might be used for medical imaging, for detecting underground resources, for navigation systems that don't rely on GPS, or for fundamental physics experiments testing the limits of quantum mechanics and general relativity. Quantum computers, if they can be scaled up successfully, will be able to solve certain problems exponentially faster than any classical computer. They could break current encryption systems, threatening security, but also motivating the development of quantum-resistant encryption. They could simulate quantum systems, helping design new materials and drugs. They could optimize complex systems, improving logistics and financial modeling. They could potentially revolutionize artificial intelligence and machine learning, but building practical quantum computers is extraordinarily difficult. Quantum states are fragile and easily destroyed by environmental interactions. Quantum computers have to be isolated from vibrations, electromagnetic fields, and heat. Many operate at temperatures close to absolute zero, and even with careful isolation, quantum states only persist for brief periods before decoherence destroys them. Scaling up from the small quantum computers we have now to large ones that can solve practical problems is one of the major technological challenges of the 21st century. Yet progress is being made. Companies like Google, IBM, and others have demonstrated quantum computers with dozens of qubits. They've achieved quantum supremacy or quantum advantage, performing specific calculations faster than classical computers. These are artificial problems designed to showcase quantum advantage rather than practical applications. But they demonstrate that quantum computers are real and working, not just theoretical speculation. Within your lifetime, quantum technologies will likely become more prominent, moving from specialized laboratory equipment to everyday applications. The quantum revolution that began as a purely scientific endeavor to understand nature's fundamental laws is now becoming a technological revolution that will reshape society in ways we're only beginning to imagine. But even if quantum mechanics never had any practical applications, it would still be worth understanding for its own sake, for what it reveals about the nature of reality. The fact that it also enables transformative technologies is a bonus, a reminder that pure science, driven by curiosity about nature, often leads to unexpected practical benefits. Rest now. Let these thoughts drift away. You don't need to remember them or understand them fully. Just let them be gentle background as you sink deeper into sleep. At the very frontier of physics, researchers are exploring whether quantum mechanics needs to be modified or whether there's an even deeper theory beneath it. One area of active research is whether gravity might cause wave function collapse. The idea is that when a quantum superposition involves objects in significantly different gravitational fields, or when the gravitational field of a superposed object becomes ambiguous, some kind of objective collapse occurs. Roger Penrose has proposed that gravity causes wave function collapse when the space-time geometry associated with different parts of a superposition becomes too different. Since mass curves space-time according to general relativity, a superposition of different mass distributions corresponds to a superposition of different space-times. And Penrose suggests there's an objective threshold where such superpositions become unstable and collapse. These ideas lead to predictions that might be testable with sufficiently sensitive experiments involving increasingly large quantum superpositions. Experiments putting larger and larger objects into superposition, while technically challenging, are progressing. If we can create superpositions of massive enough objects and study how long they persist, we might be able to test whether gravity causes collapse and whether quantum mechanics needs modification. Another frontier is quantum cosmology, applying quantum mechanics to the universe as a whole. If everything is quantum, then the universe itself must be described by a quantum wave function. But what does that mean? There are no external observers to measure the universe. The wave function of the universe seems to demand a different interpretation than wave functions of subsystems. Some cosmologists work with the Wheeler-DeWitt equation, a kind of Schrödinger equation for the universe. But this equation is timeless, raising puzzles about how time and change emerge in quantum cosmology. The many worlds interpretation might be natural here, with the universal wave function describing all possible histories of the universe, all equally real. Or perhaps we need new ideas about what the wave function represents when applied to the cosmos as a whole. Quantum mechanics might also shed light on the beginning of the universe. In classical general relativity, the Big Bang is a singularity where the equations break down, but quantum mechanics might smooth out this singularity. Some quantum cosmology models, like the no-boundary proposal by Hawking and Hartley, suggest the universe has no beginning in the usual sense. That time itself emerges gradually from a timeless quantum state. These are speculative ideas, at the edge of what we can currently test. But they show how quantum mechanics, combined with our theories of gravity and cosmology, might eventually give us a complete picture of reality from the smallest scales to the universe as a whole, from the earliest moments to the present and future. We're not there yet, but the progress made over the past century gives us hope that continued work will bring deeper understanding, and maybe someday, a century from now, people will look back at our current puzzles about measurement and interpretation the way we look back at the puzzles that confronted physicists in 1900. They'll have a deeper theory that makes everything clear, and they'll wonder why it took us so long to see it. Or maybe they'll still be grappling with these same questions, having discovered that reality is even stranger than we currently imagine. Either way, the journey of discovery continues.